to Gerard.
All right. Thanks, Peter. Hey, everyone. Hope you're doing well. Today, I'm going to be talking about this paper, ColPali, which is around, as it says in title, document retrieval using vision language models. This paper builds on, so it's really about like retrieval of documents, which, as we know, in this kind of this day and age, in this current zeitgeist, is a very popular topic as it relates to like retrieval augmented generation with LLMs. We know that having better making having better retrieval to feed into LLMs when you're asking questions or trying to get them to do a certain task has a big impact on like the quality of the task. And it builds on a few different bits. So the first bit, which I'll talk about in more detail in a bit, is Colbert, which is quite a cool paper. I think might have in a previous paper club like talked about it. It's a method for doing retrieval over in the Colbert's case just text, but using late interaction. So I'll talk a little bit about that later in the paper. But it also builds on some advancements in like vision models, and it's particularly vision language models. So the particular model they use here is PaliGemma by Google, which is a vision language model that they've trained with Gemma 2 billion as the language model, and then they use a vision transformer as well to embed the images before feeding them into the LLM. And basically, putting that together, what the authors here have done is they sort of posited this like hypothesis of like, a lot of documents in industry are not just text, right? We deal with lots of rich information, be it tables, charts like this one here, images, and usually documents tend to be like a combination of those things. And what that means is like when we want to do retrieval, usually we have to create quite complex ingestion pipelines to be able to process documents. And I'd love to hear from people here, like if they've had experience with this and what they've been doing to deal with that. I know we've been dealing with that at Mplan. And so their hypothesis, like, can we treat these documents effectively as like images, and leverage the power of like vision language models to get some kind of like document representation by treating it as an image, and being able to surface the right document or the right part of the document based on a query. And they show quite promising like results of this. So I'll talk about those later. What I thought was quite cool about this paper is actually like it's so that there's some, if you're interested in diving deeper, the authors have like a cool webinar where they talk about the paper, and it's actually like a collaboration between academia and like industry. So the main author is like doing a PhD, but like funded by this company, and I think that actually shows in the paper. Like it seems it's like extremely practical, I thought, which I like obviously as like someone more in industry, and yeah, and so I think it's an interesting. I think it creates like more interesting results because it's so focused. It seems just very focused on like practical use cases, and it considers like the trade-offs between like performance, quality, like memory requirements, all of that. They talk about that, like scaling. So I think it's quite nice from that perspective. And everything is open sourced, so you can go play with it on Hugging Face if you're interested. Cool. As Peter said, please feel free to interrupt me and ask questions as I'm going. So as I mentioned, I think one of the key like motivators for this paper is that there's a lot of like work being done in retrieval augmented generation, and the retrieval part of it is like a super important part, right? Making sure that you're fetching the right context to feed to an LLM um, to answer a question or perform a particular task. And a lot of like the a lot of effort is put into the actual document processing. So they mention here like the way you sort of maximize performance these days is really about like improving the data ingestion pipeline rather than having like a better embedding model. Like embedding models, you get some marginal gains from slightly better embedding models, but the reality is that the better you process your document, chunk it, how you deal with tables, figures, things like that makes a huge difference on your like retrieval augmented generation pipeline. And the state of the art at the moment is basically using a mix of PDF parsing, layout detection, OCR, and then also doing some kind of like captioning. For example, if you have like a figure, you could use a vision language model to like caption the image, and you can sort of store that as well in like a vector database for retrieval. Chunking strategies are like super important, right? To make sure that you're creating vectors that have like good meaning. So if you have like huge chunks, then your vector, there'll be too much information to compress into like a single vector, so the retrieval will suffer. But you obviously want it to be like manageable. So yeah, as they mentioned, optimizing the ingestion pipeline is the thing that gets you like to the higher performance these days. And here, this is kind of what like your standard PDF like retrieval would look like these days. So you have like a PDF which has a mixture of text and images. You might run like OCR on it to pull out like the text, and you might do layout detection as a way of improving your chunking, right? So you might like choose to create chunks of like relevant headers and sections, and you might use another model to like caption the image. You would then embed all of these different parts, store them. So this is all offline, right? And then online, when you have a query, you would then do like a similarity computation. So like usually like cosine similarity of the query embedding and all of your document embeddings, and find the one that most matches the query. So benefits of this is like the actual querying is really fast. And so you can do all of this processing offline. So when someone uploads a document, you can run this, and then a few seconds later you can start querying. I'll get back to their method in a second. So what they do in this paper, they have like two contributions. So the first is they actually create a whole new benchmark called Vidori. I'm going to call it Vidori, which is Visual Document Retrieval Benchmark. And the point of it is basically to create a data set that contains these kind of rich documents which contain text and images. And because that's really like what they're focusing on. And it's basically you have like document query answer triplets. So you have like, actually, no, sorry, you have query documents. So you would have like a query, and the aim of the task is to basically retrieve the most relevant document based on that query. So the first is they did quite a bit of work on creating this data set, and the second contribution is obviously ColPali, which is the model architecture they created to do retrieval on rich documents. So yeah, as I mentioned, this is the problem formulation. So you have a query and you want to find the document that is most relevant to that specific query. And this is what I was mentioning earlier in terms of like I really like how they focus on these kind of what's a property of like an efficient document retrieval system. So they mentioned it should have obviously high retrieval performance, it should have low latency in querying, and then high throughput during indexation. So ideally you want those three things, and that gets you like a good retrieval system. So there's a bit of background into like retrieval and how retrieval has evolved. And this is quite useful to understand like their sort of contributions. So at the like most basic level, but it still works surprisingly well, is like you can have statistical methods for like retrieval. So BM25 is super popular to do like sparse embeddings and retrieval on that. But obviously,
I found it really interesting that unstructured plus BM25 was like near as good performance on a lot of the benchmarks. Like, because it seemed, I think that's almost completely statistical based as a method.
yeah, and I think this alludes to like their point in the introduction, right? Is that if you have a really good way of processing your document, the embedding, the actual like quality of the embedding is less important. So they argue is less important than like how you chunk and process the document at the beginning. So if you manage to extract the text in a very reliable way, then BM25 works really well. And actually the difference between BM25 and like a dense embedding is not that different. So that's like probably what's most used these days, right? Like you might like have a document, extract the text, embed that, chuck it in a vector database or something like that, and then you can do semantic. You can do some similarity search over those vectors. Kind of taking a step up, you have like you have different retrievers. Here they call neural retrievers. So in these like by encoders, they call them, you have like you map like the documents to like a vector space, and then you take the query, you embed them, and then you do like a cosine distance. You can also do a cross encoder system, which is basically where you have like the query in the document vector, and then you pass them through like a model, and that gets you like a score for each combination. But that's obviously slower, right? Because you have to run this for every query and document. It's much slower than just doing like a cosine distance computation. And but there's another method, which is what ColPali is built on, which is this method of like late interaction. And I will just quickly share my screen, change what I'm sharing to this diagram, which describes ColPali. Apologies for how fuzzy it is. So the ColPali is super interesting. And so in like your standard methods, what you would do is you take the whole query and the whole document, you would embed them. So you have one vector for the query, one vector for the document, and then you do cosine similarity on them. For this late interaction, actually what you do is you take each token of the query and each token of the document, and you embed them. And then for each query token, you find the max similarity against over all of the document tokens. And you do this for each query token, and you sum it all up. And so what that gets you is like a much more, it's sort of much more granular. So rather than like pooling the entire document into like one vector, you're able to like have much more granular like interactions between like specific tokens in the query and specific tokens in the document. And then you pull that, and that's sufficiently fast because obviously you're still creating the document embeddings offline. So it's kind of similar to cosine similarity, but with a slight like computation overhead, like you're just doing all of these different operations. And so this is what ColPali paper sort of introduced, and this is like what they rely on in ColPali. So I'm going to go back.
And does it consider like phrases as opposed to individual words?
As far as I know, it's like
Tokens, sorry.
It's like tokens. So
Okay, got you.
yeah, so I don't know. It's a good question. I don't know exactly like how they tokenize. But it seems to be that they just do like a dot product of like one query token against all of the document tokens and find the one that is the highest dot product, and then they sum all of those up. Cool. So as I mentioned in the beginning, so the late interaction is like a fundamental part of like this paper. It's not something that's introduced in this paper, but it's a big component of like the ColPali architecture. And the second bit is the vision language models. So in this case, they use PaliGemma from Google, and basically, actually, let me also share my screen and show you PaliGemma architecture. I think it's interesting. So PaliGemma is a architecture that combines an image encoder that gets projected onto like the same dimensional space as like the text space. Those get concatenated. So you have like a text input, you have image input. Those get concatenated, and then it's fine-tuned, I guess, to output some text. So PaliGemma is like it's been pre-trained on a lot of like image and text data, and the things it can do is, for example, like captioning or like questions, so answering questions over like an image. It can even do like object detection and things like that. I think they have some examples here. Yeah, where like it outputs like a token, a special token for coordinates. So these are like really interesting models in terms of combining image and text, and that's what the paper, that's what ColPali uses for their architecture. So now if I go back to, sorry, I've lost the paper on my screen. There we go. So if I go back to this image, now I can maybe describe a little bit more what's going on here. So ColPali, what they do is you take like a document. In this case, a document is like a page of a document. So like, let's say you have a 20-page PDF. Each page would be treated as its own document. And what you do is you create, what they do is they create patches of the document. In fact, I think they create 1,024 patches per document, and they encode each patch using the vision encoder. In this case, it's SIGLIP. So in the PaliGemma architecture, that's like the vision encoder. And then they project it onto the text space, and then use an LM to like encode, to create the embeddings. So you'd end up with, for each page, you'd end up with 1,024 embeddings. And then at runtime, when you actually have a query, you embed each token of the query. So in this case, what our VITs would be each be a separate embedding. You do the similarity score, the max similarity score of that token embedding over all of the document embeddings, and then you sum them all up, and that's the similarity score of the query to to the document. So what that allows you to do is like the offline processing is much, much faster, because we're not having to do these expensive computations like OCR or layout detection, which is straight up passing 1024 images through like an encoder, through an LLM, and getting out the embeddings. There is a slight overhead when it comes to the actual doing the actual like similarity score computation, but it's marginal compared to the gains that you get in the offline processing.
Did you find any further discussion on why they use maxSem as opposed to average sem or some other?
No, I didn't. I'm pretty sure that's what they used in Colbert as well. There might be an answer in there, but they don't discuss it in this paper. Cool. So I think I'll gloss over the data set if you're interested in that. There's more there, but basically the data sets they use, they try to have a variety of data sets, some from more like academic environments, academic tasks, like question answering over documents. But they also created more like, they extended the data set with some like industry documents that covered like different sectors. And I think one thing to note that's quite interesting is they used Claude 3 Sonnet to generate queries for those documents. So they'd feed like a page into Claude and say generate a question and answer pair for that document. And that's how they sort of synthetically generated more data for this benchmark. And they tried to have a range of like documents that were more text heavy and documents that were more image heavy. And you'll actually see, it'll be really easy to see which ones are more image heavy and which ones are more text heavy in the results. So they compare quite a few like models. So they show, they compare like their new system to current systems, and current systems are like what we've described in terms of like document ingestion pipelines. And so they use the unstructured library to do that. So they do just like different methods. They have 3. So it's unstructured just on text. They have unstructured with OCR on like tables, charts, and images. And then they have unstructured plus captioning, where they take figures and pass them through Claude 3 Sonnet to get like a description of the chart, and embed those as their own chunks. And then for good measure, they also add in some retrieval using just like off-the-shelf VLMs. Cool. So maybe go into the results to show you what happens. So I think before we go into their results, I think some things that are quite interesting are that, so as Peter mentioned before, the difference between the dense embedding model and the sparse embedding are not that different. So 67% to 65. And it's clear that like having captioning improves a lot. Well, not a lot, but it definitely improves over just text. So there's obviously like important information in the images that we need. And then you can actually see a little bit like which data sets, as I mentioned, which data sets are more visual heavy and which are more text heavy. So the archive ones, you can see that the this VLM performs fairly pretty well on archive, because presumably it can understand the images in the documents pretty well, but it performs atrociously. Oh god, it performs atrociously on this data set shift, which they talk about. Not sure if they talk about it in the paper, but they definitely talk about it in their webinar, where this is quite text heavy. So the shortcomings for VLMs is that they struggle when the documents are text heavy. So there's a large variation in the performance in the test sets, in the data sets, sorry. But then looking at ColPali, it can do it does the best or tied the best on the text data sets and performs extremely well on on all different data sets. In fact, the difference between them and the other methods is pretty crazy. And they're able to do this because the late interaction that I showed you is differentiable, which means they're able to train this whole thing end to end. So they have they create a sub data set, and then they can basically train it to be able to achieve this retrieval task. And the vector space they use is not the embeddings are only 128 dimensions, which I guess is why it's pretty fast. Even though they have 1024 vectors per document, it's still pretty fast to compute the dot product over all the query tokens and all of the document embeddings. Yeah, so I was pretty, yeah, Dwayne?
Sorry, I was just doing some back of the envelope calculations, and there are 650 archive papers a day, and this would take about an hour and a half to ingest them, which to me seemed pretty good, and it cost you about $1 to run the an hour and a half for the GPUs in the machine on Google GCP. So this is quite a quick. It's efficient.
Yeah.
I just thought, I just thought I'd share that.
Yeah, thank you. Yeah, I think that's really a big point of this is as you can see here, actually doing the encoding for a document is really fast compared to if you need to run layout detection, OCR, and then on top of that do captioning for figures in a page, which uses a different LLM or VLM. So that's a huge benefit. There's still a question for me about, and I think there's been follow-up work to say okay, so what you retrieve from this is a document, which is still just an image because you haven't processed it. So then afterwards, what do you do with that image? Now, these big model providers like GPT-4o and Claude 3.5 and stuff, they all have image capability, so you can feed an image into the context. So potentially it's a sort of new paradigm, rather than running OCR and feeding text into the context, it might actually be better to just feed an entire page, a page, to the LLM, with
You
like
know,
figures and
one thing
everything.
I was wondering is like, how does the number of patches affect the performance? I think they have that somewhere, but because to me, I'm like, when
Yeah.
you segment the page, you're gonna you're probably gonna have, if it's 1024, that's like 100 by 100. I'd be surprised if there were like even letters that were cropped, so you had half of a letter,
Yeah.
and somehow the model is still able to make sense of the whole thing. Which
Yeah.
is
I'm
impressive.
quite shocked at that as well, to be honest with you. So they showed here they actually did run it with 512 patches, and the performance degradation was quite like severe. So it lost like 30% on this like ranking metric. But it's really interesting. So they show at the beginning, what you can do actually is like, because you've chunked the document and you can compare like the query tokens to like all of these different patches. You can see which patches are the ones that are like most important to the query. And so that's what they show here, right? So in this case, the query is which hour of the day had the highest overall electricity generation in 2019. And if you take this token hour, it shows you which patches have the highest similarity. Yeah, definitely. And it's so interesting, as you said, like, you know, that it's tiny patches, but it can figure out that like, well, things like, you know, 20 might be an hour, like it figures out that hourly this whole thing seems like activated. And then the x-axis as well, like all of these numbers respond highly, or like they have high similarity with the token hour. And actually in the appendix they have some more examples as well, which show that these vision language models have kind of OCR capabilities. Let me show you. So this is another example where in this document, the token Kazakhstan, it seems to find like the words Kazakhstan in the document, or words that look kind of similar. So there's kind of there is some kind of textual understanding, because it can take the token for, or the word Kazakhstan, and find the patches where the word is mentioned in the image. And it also, that, you know, this is a French document, so one thing they also wanted to show is that it generalizes to some other languages.
But I did feel like that component of the paper didn't make a ton of sense to me, because paper itself, in my opinion, is about processing documents that have visualizations in them.
Yeah.
And being able to do that more effectively. So I don't really think it matters if you can do it in French versus English. So like the fact that it does do worse on one language than the other is actually, in my opinion, a distractor from the point of the paper. And they mention it a couple of times, and I was thinking like, this doesn't really add anything to what they're trying to show.
Interesting.
Yeah.
I mean, I wonder if it was a general like, so because the company that did this is based in France, and the students based in France, I think, as well. And so it might be like they had a particular interest in being able to show that it performs across French and English for their own use case.
That would make sense, actually.
Hmm.
That there is a, yeah.
But I guess the interesting thing is that just like, because these documents are just images, so the text is just like pixels. And so the fact that it can sort of grasp concepts in different languages from like pixels is I don't know, it still blows my mind sometimes that these things work. Yeah, so they show so yeah, they do a few like different variations. So we mentioned like reducing the patch sizes. They also compare to like using a different VLM, which so they use PaliGemma 3B, but there's a different VLM called Idefix 28B, which is based on Mistral 7B. And what it gets like quite similar performance, but with 64 patches rather than 1024 patches. Which what they suggest here is that like the language model size has an impact on performance, but doing like with much smaller number of like image embeddings. But then there's a performance trade-off, because doing 1024 patches, but like with a smaller model, is quite fast, like compared to using this like larger model with less patches. So there's some trade-offs there, and then interestingly as well, I think is the fine tuning, right? So you can, this is a retrieval method that can be trained end to end because the loss function is differentiable. And so they show this by fine tuning on like this French yeah, so there's this data set which is like French tables. So there's like tables in French for like question answering, and they add some more examples to the training set and show that the performance like does indeed like improve, and the recall at 1, which is I guess what they care about, is like finding the one gold standard document increases quite a lot. The one thing I didn't understand, and I was trying to look this up in Colbert and like other explanations, but this query augmentation, they sort of briefly touch on it, where they say they add here. So they add 5 unused tokens to the query tokens. They say to serve as a soft differentiable query expansion or reweighting mechanism. I'm not really sure what that means.
I wonder if it could be. Remember the like last year there was this big paper about how if you add on 4 tokens to the beginning of a transformer when you train it, and then you always add those in. Oh, no, what was that called? Yeah. But it was essentially that when you're doing window detention in order to save on time.
It's like anchoring or something.
Yeah, anchoring or something, and you want to still have like some tokens that that are the beginning tokens of the. You still want to include in the window the beginning tokens of the sequence, because otherwise the model just its performance degrades because for some reason it needs access to those tokens. Let me see if I can find the paper.
Yeah, it'd be interesting to look at. I kind of thought like, because if every query token gets compared to every document token, you have like a max similarity. So I wondered if like these five tokens, they mentioned weighting or like reweighting, because I guess like you compare them to all the document tokens and then you sum it all up. So I don't know if it like balances, if it's, yeah, I don't really know what the kind of effect it has, but it sort of adds something to the similarity score.
Attention sinks, that's what they were called.
Oh, cool. Thanks. I'll have a look. But yeah, I'd be curious. That's kind of the gist of the paper. There's some more interesting things like in the appendix if you want to dive deeper on any particular area. I think one thing to note, as they mentioned here, is that this kind of late interaction is not as widely supported as just like your classic similarity search. Or so if you want to implement this in production, you might have to find some vector databases to support it, or find other ways to deploy it. If you want to play around with it, I know DSPY, the library for programming with LLMs, has like a really nice. A lot of their examples use callbars actually. But I'm curious, are people in the call, like, do you work with kind of parsing PDFs, like rich PDFs or PowerPoints or documents or things like that, and how do you do it these days? And is this something that you would be interested in trying? And if not, why not? Yeah, go for it, Dwayne.
We don't at the moment, but it's on the roadmap at WiseWorks, and so it's really for presentations inside meetings, doing this kind of processing, so that we can get hold of, so we can index and find what the content is.
Mm.
Yeah.
I was wondering if we could use this. Well, not. I feel like it's a little bit. I don't think it's a great idea, but I was wondering if we could use it to do like to train a video model. Like if you have something that understands text and image, then put that in, like put the subtitles and the text together, and maybe we create like a foundation models for videos that has a lot of capabilities that we never thought of. I thought that could be cool.
Yeah, Lewis.
Yeah, sure. So it's not something that I sort of do in my day-to-day, but I did sort of for my Medium blog look at creating. It's essentially a grant application writer. So I mean, I work in publishing, generally speaking, and I use Gen AI to write articles, newspaper articles. But yeah, for my Medium blog, I did a small project to sort of ingest academic papers with a hope to use like an agentic workflow to create grant applications. It was a bit of fun. It performs reasonably well, but it's not. It would be interesting to see, yeah, how this would perform. Essentially, I think that's my mind back. I think I just used pages and then just segmented the text. Yeah, I didn't do anything super sort of sophisticated, but yeah, it would be interesting to see.
Yeah, absolutely. Yeah, I think academic papers are a really interesting one, just because they have a lot of rich data. Yeah, Thomas.
Hello. Yeah, thanks for walking you through it. In terms of whether we use it, actually, yeah. So we have a like vast knowledge bases when we work with clients. All this like private notes or code that's all over in our SharePoint. And right now, what we're doing is kind of early stages, but we're splitting it into document types. Let's say, yeah, PowerPoint versus an Excel. And we're still in the brainstorming phase of how to, let's say, extract relevant data points from an Excel file
Yeah.
Or if it's a PowerPoint, how do you extract text if it's been copy and pasted?
Yeah.
This seems quite interesting. I think for now we were looking at Gemini, Google Gemini, because it's
Yep.
built because we're building on Google Stack
Yep.
anyway, right? But this is all done through Hugging Face. You would deploy this.
Yeah, exactly.
Or, yeah.
So they have yeah, you can actually go on they have a demo on Hugging Face if you want to try it out. Here, let me share. Sorry, lost my mouse. Yeah, so you can try it out here where you can I've tried it, it's quite good. So you can like upload some PDFs and then yeah, and then have a query and it extracts the documents. I've tried it out with like a one of Nplan's case studies with a client and just asked it to find like testimonials, client testimonials and stuff, and it's pretty good at pulling those out. So yeah, definitely gonna play around with it more, and particularly when it comes to like Excel's is like a funny one, and one we've had trouble like dealing with in the past in terms of parsing, because there might be lots of like tables and subtables within sheets and all of that stuff. So it's interesting to know how to embed that.
Yeah, thanks, man. I'll try it out.
Yeah.
I wonder if in the future we'll come up with ways of embedding documents, because the other issue you might have here is the one that like a good embedding for retrieval might not be a good embedding for summarization. That's one of the papers we did recently, in fact.
Yeah.
So I wonder if we'll have embedding methods that give us like a general embedding where it's possible to extract a lot of different types of information.
Mm.
Yeah, I don't know. So like, for example, with the Excel, you embed an Excel document and you can figure out like what the headers are, but also ask like, I don't know, what's the mean of this of the average temperature in this column or something.
Yeah. Cool. Thanks, everyone.
Thank you.
Yeah, thanks. It was good.
Thank you.
Good paper.
Thank you very much.
Thank you.
Take care.